So where we left off was the Newton discovering that the Earth's gravity reached all the way out to the moon and was responsible for the moon that was traveling in a orbit around the Earth. Okay, and so what makes the Earth and the Sun so special? The Earth travels around the Sun in much the same way the moon travels around the Earth. What makes the Earth and Sun so special and the Moon, that they have this invisible force of gravity? Nothing more special than the fact that they have mass. And what else has mass? Well, virtually everything around you, including the air. So what does that mean as far as gravity goes? Well, if I were to ask you if you were attracted to the person next to you, the answer would be yes. You are physically attracted to the people around you because you have mass, they have mass. Therefore, there is a physical gravitational attraction that is attracting you to one another. Okay? So Newton didn't discover gravity. He discovered that anything that has mass attracts anything else and everything else that has mass in the universe. Okay? So if you picture using the Force like in Star Wars, if there was no friction on the table, you could pull your pencil to you, not by magic or using the Force, but by gravity. It would take a long time, but it could be done. Okay, so Newton's coming up with his universal law of gravitation. So he wants to put this in mathematical form. And basically what he discovered so far was that the force of gravity was proportional to the mass of the first object times the mass of the second object divided by the distance squared. So it's only proportional to right now because we're missing a certain computational factor that we gotta get in a little bit. Okay. One thing to note, when we talk about the distance here, this could be a d, it could be an r. You might see it different ways. D is the distance from the centers of these objects, the center of masses. So that is an important distinction. Now, this is the force of gravity on each object. Notice that this has the mass of 1 and the mass of 2. So if I'm trying to figure out the force of gravity on object 1, it's this equation. If I'm trying to figure out the force of gravity on object 2, it's the same equation. They have the same force of gravity acting on them, even though they've got different masses. Okay, they've got the same force of gravity from one another. Okay? Remember Newton's third law that when 1 pulls on 2, 2 pulls on 1 with an equal and opposite force. Okay, so this is a direct consequence of Newton's third law. So if I were to ask you, here we've got the big Earth and here we've got the much smaller moon. They pull on one another, and I would ask you which one feels the greater force of gravity from the other. Okay, would it be the big Earth or would it be the big moon? Okay, or the little moon. Okay, and the answer, if you remember what we just talked about, is it would be the same. Okay, they exert equal but opposite forces on one another. Okay, so let's see what would happen if I doubled the mass of one object. Okay, if I double the mass of one of these objects, there's going to be twice as much mass on top, and that's going to cause the force of gravity to double. Okay, so if I double the little one, okay, the force of gravity is going to double between them. Okay? And compare the force of gravity between the Earth and a 1 kilogram object and the Earth and a 2 kilogram object. Well, the force of gravity on the 2 kilogram object is going to be twice as much as the force of gravity on the 1 kilogram object. Well, duh, it has twice as much mass, it's going to weigh twice as much. Really, we're talking about weight here. Okay, let's say I double the mass of both objects. So I double the mass of mass 1 and I double the mass of mass 2. Well, I'm going to double this and then I'm going to double that. Okay, so I'm going to end up with quadruple the amount of force between them. Okay, so times 4. Okay, quadruple. Okay, let's see what happens if I double the distance between the objects. So we're going to double r, or d as you might see it. Okay, so let's go ahead and double the distance. Okay, and now I'm going to double this on bottom. Now, when I double this, remember that it's squared.
So that double is going to become a 4 times. Okay, so I'm going to have a times 4 on the bottom, which means it's going to be 1/4. Okay, if the 4 is on the bottom, it's 1/4, right? Okay, so if we double the distance, you decrease the force of gravity by a factor of 4. Okay. If everything attracts everything else, why isn't this more obvious? The mass, okay. Well, the attraction between normal size objects is extremely small. Okay, the attraction between you and your pen is trivial. Okay, it takes something really big for the force of gravity to become noticeable, because gravity on the whole is actually a fairly weak force. Okay, so if we're talking about the force of gravity between a 1 kilogram object and the entire Earth, which is pretty big, okay, it's only 10 newtons. Okay, only about the weight of 10 apples. So that's why it's not more obvious from everything. Okay, how big will the attraction be between two 1 kilogram objects? So if we replace the entire huge Earth and replace it with a small little 1 kilogram object, how big of the attraction will that be? And there won't be hardly any force between them at all. Okay, so what we were looking at was a relationship. So if I double this, what happens to this? In order to make this an official equation, we need a number that makes all the other numbers work out. So when I plug in mass in kilograms and mass in kilograms and distance in meters, okay, I want this answer to work out so I get a force in newtons. Okay, and this fudge factor is G, the universal gravitational constant. Okay, now, we don't know what this is yet. Okay, we don't know the mass of the Earth and things like that. So, in order to figure out what big G is, universal gravitational constant, I would need to know all the other numbers, okay, and then I would just plug them in and calculate what G is. Okay, I need to know the mass of one object, the mass of the second object, so that's not too hard. Okay, I need to measure the distance in between them. Okay, that's no big deal. Okay, and then I would need to know the force of gravity between them. Okay, well that's a little trickier. Okay, if I deal with objects that are normal size, like a 1 kilogram object and a 2 kilogram object, and I put them 1 meter apart, the force of gravity is going to be so weak, I'm not going to be able to measure it, so I'm not going to be able to get this number. Okay, or at least it will be very difficult. Okay, let's put it that way. All right. So the force of gravity between normal objects that can be weighed is very, very weak. How to measure? Well, along comes a guy named Henry Cavendish. He's kind of a quirky individual. He was very shy, kind of your absent-minded professor kind of guy. He was terrified of women, and in his manner, he had a separate set of stairs made so that he would never have to come in contact with his women servants. Communicated with them only by notes. Okay, and apparently he dressed out of date even for the time that he was in. Okay, he came up with this pretty cool experiment which would measure the very, very weak force between normal size objects. And what he wanted to use to measure this very, very weak force was just the twisting of a thread. Okay, this quartz fiber. And he came up with a deal where he bounced light off of a mirror that was connected to that, and that light would shine on a distant scale, and that would this light on this distant wall would magnify the twisting of the fiber, even though the twisting of the fiber is very weak. Okay, he comes up with a number pretty close to 6.67 times 10 to the minus 11. That's what we recognize G, big G, to be today. Okay. Now notice that 6.67 times 10 to the minus 11. Okay, that's a pretty small number. That's what this looks like in decimal form. And it's a small number because gravity is a relatively weak force. Okay, so this is the equation we know now as Newton's universal law of gravitation, which is the same one before, except that we've got big G in it. So this big G is a constant, which means you always put in this number for big G. Okay. All right. So now that we know big G, we're able to use what we already know to figure out the mass of the entire Earth. Because we don't know what the mass of the entire Earth is. Okay, so what they do is they plug in a number they figure out, they come up with some weight, let's say a 1 kilogram object. Okay, we know big G. They knew the radius of the Earth. I'm not exactly sure how they knew that, but they were pretty clever folks, kind of like they're being pretty clever here. They know the weight of that object compared to the Earth, which is 9.8 newtons, and they solve for the mass of the Earth. Okay, and the mass of the Earth is 5.98 times 10 to the 24th kilograms. All right. So Cavendish's experiment is often called the weighing of the Earth experiment because it allowed us to, and that's kind of a misnomer because we didn't really calculate the weight of the Earth because the Earth doesn't really technically have weight because weight is a force of gravity. And what we calculated was the mass of the object, or the mass of the Earth. So around 1850, another gentleman, Philip Van Jolly, used a much simpler apparatus and came up with some more accurate results. But I gave you the number that's recognized today as big G. Okay, let's use the equation here. What is the force of gravity between a 65 kilogram student sitting a half a meter away from a 75 kilogram student? Okay, so big G is 6.67. So what we want to do is just plug the numbers into the equation. 6.67 times 10 to the minus 11th goes in for G. The mass of the first student was 65 kilograms. And it is important to note that all of this has to be in kilograms and meters. Okay. The mass of the second student was 75 kilograms. And the distance between them was 0.5 meters. And then don't forget that we got to square that. And you should get 1.3 times 10 to the minus 6 newtons. Now, I suggest that you actually go through and type these numbers into your calculator and see if you can get the actual answer. Because when we're working with scientific notation and math, it's pretty easy for students to make simple mistakes, and then that'll cost you on the tests and that sort of thing. So, and what we find out is the force of gravity between these two students is basically a millionth of a newton. So if you were to take an apple and cut it into a million pieces, the weight of that teeny weeny little piece would be the force of attraction between them. All right, so take a moment and plug this into your calculator, pause it, and then come back and see if you get that. All right. Let's work one that's a little bit more challenging with the calculator. The math the equation's still the same. What is the force of gravity between the Earth and the planet Mars at their closest approaches? Okay, which is 1.01 times 10 to the 11th meters between their center of masses. Okay, I give you the mass of the Earth, which I gave you before, and I give you the mass of Mars. Okay. So let's go ahead and plug this into our calculator. So big G, 6.67 times 10 to the minus 11. Okay, go ahead and you might want to pause this and see what you get here. Times 5.98 times 10 to the 24th. Times 6.41 times 10 to the 23rd. And then now notice that I put this in parentheses on bottom. Okay. When you're dividing by this, I strongly suggest you put parentheses around this and then square it. And you should get 2.51 times 10 to the 16th. If you didn't get that, email me or come to my office meetings and we'll see if we can't get you figured out. All right. Last problem. What is the, hold up, is this? Yeah, we'll work this one. Okay, sorry. What is the force of gravity between the Earth and a 5 kilogram object, which is this many meters, which is 2 Earth radii above the surface of the Earth? Okay. Given that the radius of the Earth is 6.38 times 10 to the 6, or 6.38 million. Okay. We're given the mass of the Earth and the radius of the Earth. Now, the trick here is that it is 2 Earth radii above the surface of the Earth. So what we're talking about is, so we're at the surface of the Earth, we're already 1 Earth radius away from the center. We're 2 above that. So how many Earth radii are we away from the center of the Earth? If we're 2 Earth radii above the surface, we're 3 away from the center. Okay, which is why down here I put 3 times the radius of the Earth. And again, notice that I've got this in parentheses and then it's squared. Okay, And the top is just the familiar players, big G, the mass of the Earth, and then 5 for our 5 kilogram object. And again, put this into your calculator, see what you get, and I get 5.4 newtons. So if you don't get that, contact me, or try to get some help. See if you can get it, figure it out. Okay. Well, anyway, have a great day.